Morris Peels, and welcome to another edition of 3D Printing News Unpeeled, courtesy of 3dprint.com. Today we've got a number of additive manufacturing and 3D printing news items. Well, the first one actually isn't like an additive manufacturing news item. It's an opportunity. There's a German startup called DCubed, and they have announced that they're starting on the FENNEC project. So they're working together with another startup called German Orbital Systems to develop a heat management system. It's a foldable, new space, next-generation radiator for CubeSats. So CubeSats, or small satellites, are increasingly smaller, very compact, very inexpensive satellites that can do increasingly more things as microelectronics improve, as computers get more commoditized and more powerful. And they can really leverage that into, well, perhaps bringing to the satellite revolution really inexpensive paths to space. What I like about DCubed is what this company is doing is it's making components for these satellites. So you can basically go to them like you would like a supermarket or a wholesaler. They have, for example, a space selfie stick, which is going to enable your satellite to record itself. They have a solar array you can buy. And these guys can basically, you have a library of parts, or a small library now, you can buy from them. And then that'll accelerate your own CubeSat development. So you don't have to do everything. You can just buy these components from them. So I think this to me is a force multiplier for this new space industry, where you're saying, a lot of American startups want to do everything themselves. They're completely vertically integrated, and we make the rocket, we make the production technology, everything. But this is a company that's saying, no, we're going to make these components, and everyone else can use them and buy them to not have to make everything custom. Now, this is supported by the DLR, the German Space Agency, and they're using a large amount of surface area. They're trying to get a large amount of surface area for radiators and trying to create these radiators to help the satellite cool itself efficiently. Now, this isn't, or as we know, we don't know at this point if this is 3D printed, but this points to a really decided opportunity for 3D printing companies to make standardized components using 3D printing. We know 3D printing is an incredibly advantageous technology for heat exchange, heat sinks, and these kind of things. And for a radiator type of design, we could make a lot of surface area at a comparatively doable wall thickness available to provide for surface cooling of this satellite. So this is a really big opportunity. Maybe DCubed is going to 3D print this radiator. We don't know this as of now. But what we do know is that this is something that could be of real advantage to 3D printing companies. And it should be, if we're looking at the new space market, yes, there's an opportunity to be SpaceX or a direct competitor. But if we believe this market is going to grow, then there's a lot of opportunities to make components as well. And a lot of people are focusing on launch services. But, looking at components and high-value components like RF antenna, heat sinks and stuff could be a really great way to enter an industry with a stalwart component that enables everyone else. The classic, in a gold rush, sell people the pickaxes kind of approach. The next news comes to us from HAMR Industries, which is joining the Neighborhood 91 in Pittsburgh. Now, first off, we're always interested in news from Neighborhood 91. And the reason for that is that this neighborhood is in Pittsburgh. It combines a number of 3D printing companies, Service Bureau, Metal Powder Works, which is a producer of powder, Wabtec, which is a large rail company. And it co-locates them at a campus really near to the airport in Pittsburgh. This could mean a self-supporting ecosystem where you could have a lot of advantage operating there on sharing the same infrastructure, on working together in each other's labs, on interacting with people who are doing similar things. So, we see a lot of countries trying to stimulate 3D printing. We also see cities trying to do it, like Berlin and others, Pflugerville, for example. But here we're seeing a place trying to create the infrastructure. Right, and we know that infrastructure, once it's set up, once it's advantageous, is difficult to kind of extinguish. So this means that we're really interested in this, any development in this campus. On top of that, what we're seeing is that this is, the company is the HAMR company. Isn't one really interesting? HAMR Industries essentially develops materials. And they develop these materials for all sorts of things. Gas turbine engines, hypersonics, directed energy weapons, or protection against directed energy weapons, munitions, nuclear power, solid oxide fuel cells. So this is a really, on the one hand, a really specialized company that for the military, mainly in defense, is making hardened materials using 3D printing. They use their Speed 3D printer for this often. But the things they do is really broadly applicable, as in many industries could eventually use kind of hardness components or new harder materials or coatings to make their performance better. The next thing is PPPrint makes PP available. Now, PPPrint with 3 Ps is a specialized polypropylene 3D printing company. They launched, I think, a number of months ago, and I missed this. And so I like this a lot because we don't get a lot of specific materials companies. We get like broad, really large monomer polymer companies trying to shop their whole portfolio, or we get people that are kind of specialized in a certain area. But these guys are just saying that we're all about polypropylene printing. Polypropylene is a really abundant material that has some really interesting characteristics. Makes it very chemically resistant. It's soft and flexible, which makes it a very ideal material, for example, braces or cushions, or like think of a seat cushion that could be customized, or a post-operative brace, or an item of sports equipment like a golf club handle or something. And given polypropylene is low cost, and especially these softness characteristics and the fact that it's quite tough, makes it ideal. And especially given the fact that we kind of suck at printing flexible parts until now. Yes, we can make it in FDM, material extrusion. MGF has polypropylene as well. But typically, it's quite tricky to print this material. So companies solve this by offering 12 colors of what they call their P filament, and they've optimized this filament for high layer adhesion and low warp, which is always good. They have some skin contact approvals as well, which is also a nice sign. And they have a build surface. So you can buy the build surface for them to stop your layer adhesion problems. And you can even buy a breakaway support material, all for polypropylene. And I like this kind of like this very specific companies that make very specific propositions, especially if it's a material that is used incredibly widely like polyprop. And we can see in this example, we're seeing a brace, which I think is a beautiful application for polypropylene. And then we're seeing that once the part is heated, the support material can be removed. The next examples, and maybe even a better one, there's like a finger brace. These have hundreds of thousands to millions of instances of people using them. It needs to be customized, but at the same time, it can't be really expensive. So it's a great example of what polypropylene can do. So I think the idea of having a full portfolio of things that lets you as a company or person print polyprop easily is very, very compelling. Framatome is introducing the first 3D printed fuel component. This is a component that will be installed in the Forsmark, Sweden, in the nuclear power plant there, operated by Vattenfall. And it's a stainless steel component, and it's a fuel assembly component. It holds fuel rods in place and prevents debris from getting into lower parts of the reactor. Usually this was made out of different cut stamped plates that had to be joined or welded together. Now, the problem with this is that it requires a lot of steps. This also means that it requires a lot of supervision, quality assurance, and a lot of monitoring for all of those steps. So for these guys, making the additive manufacturing process much more applicable and much more kind of like, much more easy to do because it's made out of one part and it's made out of one process. So I think that's a very exciting kind of thing to have, such a critical component that would require a lot of precision and a lot of quality assurance to get it right. It needs to perform correctly, be made with 3D printing specifically because it's easier to do this in that quality regime through making this one part in 3D printing and then post-processing it. Framatome has been working on 3D printing since 2015, and now we're seeing these parts come to the fore. So this is a long-term process, and thank goodness, because of course, if it goes wrong with these things, the problems can be manifold on time. Okay, the next thing is a very exciting paper in additive manufacturing. Letters about using laser scan speed to change the shape memory alloys. Shape memory alloys, also called 4D printing materials or lots of other things, are alloys and materials that can, through change into a predetermined shape later on. In this case, what they've done is they've taken the researchers from the EPFL, EMPA, and KIT, led by Irene Ferretto, have looked at an iron manganese silicon based shape memory alloy. Right? They're also called practicable iron-based SMAs, or shape memory alloys. And what they've done is something that is so elegant and so simple that really kind of blows me away. It's they've changed the microstructure by simply which changes the shape memory properties of the object, and in some cases the mechanical properties, just by changing scan speed. And you can see that in the graph in front of you, where the 3 different sets are different scan speeds, and you will see the different makeup of this alloy changing as the scan speed changes. So these microstructural differences can be used to deform the shape memory alloy in a different way. And what ultimately this could do, and I'm saying could because up until now this is pretty amazing already, but what it could do in somewhere in the future is to give you tailored properties at a specific location or in a specific part. Or what you could get is what is ultimately the dream material for me, is like a functionally graded material with voxel level control over properties. Right, so you could change potentially, right? This is like the far off thing, right? You could potentially change the voxel level properties of this material and how it would change shape in the future, just based on changing scan speed, which is given the alternatives, a relatively simple parameter to change. So that to me is incredibly exciting news. The next item is a component that BMW did with the Technical University of Munich. This is a component where it's a test component, right? It's not going to be on a car anytime soon, but it is something they're working on. I think it's really exciting. What they've done is they've used extrusion-based 3D printing and automatic fiber placement to produce a B-pillar mid-roof frame for the car. Now, before this was like previously was meant as a carbon fiber reinforced material made with traditional means. And in carbon fiber and long carbon fiber, well, traditionally people would think, well, can we use short carbon fiber, cut carbon fiber for this part, right? Which gives us a lot of the rigidity maybe and strength. Or do we need to go to like a long carbon fiber or continuous carbon fiber part, right? Which is more difficult to make, but might give us higher strength. Or could we use a non-3D printing technology, for example, automatic fiber placement? And what they've done here is a really elegant piece of work as well. They've essentially looked at alternatives. So they looked at using selective laser sintering or powder bed fusion and extrusion in combination, right? Where I love this. This is a solution that they ultimately didn't go for, but I really like it. They printed the complex parts in selective laser or powder bed fusion, SLS, and then they injected the carbon fiber CFRP material into these cavities made by the sintering process. I love this. I think this is a really elegant solution that you could see working at scale. Now, what they ended up going for is something using the CAD AM flexible printer, and they use just the polyamide reinforced short carbon fiber, right? Which they printed. And then they were able to reinforce this with unidirectional carbon fiber polyamide tapes using this automatic fiber placement process. So this is a very elegant combination of using a relatively inexpensive large-scale 3D printing technology, just an extrusion technology, and then in combination with automatic fiber placement. And they're taking these two technologies and combining their relative strengths. Now, the team does indicate that they need to add subtractive manufacturing into this, but it's easy to see how you could get a cell working together that combines this automatic fiber replacement, the 3D printing step, and whatever post-finishing we need to do. Another thing which I thought was very exciting in this part of research is that the researchers say that if we're looking at equaling injection molding kind of yield of 100 kilograms an hour, it's better to print 10 kilometers, this is a quote, it's better to print 10 kilometers an hour and only need to machine the surface slightly than printing, for example, 1 kilogram an hour with high accuracy. This is the same thing that led a lot of people a while ago to adopt 3D printing for turbine blades and other such things, where they went to E-beam because Avia Aero and these guys had concluded that there was faster 3D printing combined with post-processing, where you make the shape in the 3D printer and you make the part in post-processing. That was much faster than doing it via other means. So this is the guys at BMW and the Technical University coming up with a similar kind of approach, where they're saying print fast rough and the machine down is actually much better than printing slow accurate, which is, I think, a really interesting thing to grapple with if you're dealing with developing applications like I am, or if you're looking at developing a machine to try to figure out where this trade-off lies. Also, the team goes on to say that yes, they need some high tolerance, but they only need these high tolerance on the mating surfaces. So in this case, they could have, maybe inserts or other things printed there that you could maybe look at that maybe would mean that you don't have to make this whole thing with this super high tolerance. Overall, this component was lighter and thinner than the comparable conventionally manufactured one. But we need to remember for a second, this is a technology demo, right? For BMW, this is going to take quite a while for them to implement this. At the moment, they're looking at trusses for demo cars, so lightweight kind of support kind of structures, which is a very exciting area, and gripper, end of arm tooling kind of stuff. There's a lot of companies working on this, like 9T Labs, Impossible Objects, CAD, Continuous Composites, APS Tech, Mark Forge, Revo, Ingersoll, and there's more out there. And a lot of they've really been searching for applications, a lot of these guys. And these kind of structural components of cars, it could be a really very exciting area for them to look into. So that's why, this is the thing that I thought was the most exciting news of the day, although the shape memory alloy thing is also super exciting as well. But yeah, thank you for joining me again today, and I hope this was useful for you, and share it with all your friends, and hopefully you'll see you again tomorrow.